Hi, I'm Dean,
And my name is Orr.
and we're going to be presenting on fast distributed algorithms for Girth, cycles, and small subgraphs.
In the subgraph existence problems, we're given some graph G and a pattern H, and we need to determine whether and to what extent does the graph G contain copies of H. There are three main archetypes for subgraph existence problems. Existence and detection, in which we need to determine whether there exists a copy of H in the graph G. Counting, in which we need to count the number of instances of H in the graph. And listing, in which we need to output a set of all copies of H in the graph. In this example, H is a triangle. Therefore, our goal is to find triangles in the graph. In this example, G contains the following three triangles, and in a listing problem, we would need to output all of them. In our work, we focus on two main problems, the Girth problem and the 2k cycle freeness problem. In the Girth problem, our goal is to output the size of the smallest cycle in the graph. In the 2k cycle freeness problem, we're given some parameter k, which we think of as a constant, and our goal is to determine whether the graph contains a cycle of size exactly 2k. There are three distributed models relevant to our work: local, congest, and the congested click. In all three models, we have n nodes which communicate with each other in synchronous rounds. In the local model, a node may only communicate with their direct neighbor in each round, but have unlimited bandwidth to do so. In the congest model, node may still communicate only with their direct neighbor, and furthermore may only send order of log n bits per round to each such neighbor. In the congested click model, nodes may communicate with all other nodes in the network, not just their neighbors, but may only send order of log n bits per round to each other node. The goal is to find an algorithm that solves the problem in a minimum number of rounds. One trivial solution for most subgraph freeness problems, and in particular the 2k cycle freeness problem, is to have each node collect its k neighborhood and locally check whether it contains a 2k cycle. In the local model, nodes may trivially collect their k neighborhood in order of k rounds, and it is easy to see that this is an optimal solution. On the other hand, under limited bandwidth restrictions, such as the congest model, the trivial solution of having nodes collect their k neighborhood might take as much as delta to the k minus 1 rounds, where delta is the maximum degree of the graph, as each node can inform any other node of roughly only one of its neighbors per round. Therefore, the subgraph existence problems thoroughly demonstrate the gap between limited and unlimited bandwidth models. In our work, we focus our attention on limited bandwidth models, in which we look for algorithms more efficient than having every node collect its k neighborhood. In the congested click model, we showed the following results. For the girth problem, we showed that the network can compute a +1 additive approximation of the girth in order of 1 round. Our algorithm is composed of two main components: a component which allows us to have each node know all paths of some non-constant size it participates in, and the second component which allows us in a constant number of rounds to double the size of the paths each node knows. Next, we present a powerful deterministic vertex partitioning tool for the congested click called partition trees. This allows us to solve 2k cycle freeness in order of 1 rounds, as well as greatly expedite exact girth computation when we have some lower bound on the girth, for example when the graph is triangle free. In Congest, we show a new technique called cycle neighbors, which we use to obtain improved algorithms for small even cycles and exact girth, and present new circuit complexity barriers for improving the currently known lower bound on C6 freeness.
Okay, so let's look at previous works which are related to what we're doing in this paper. We'll start with the congested click. Previously, it was known how to compute a polynomial number of rounds using matrix multiplication, the girth exactly. In our paper, we show a constant round algorithm which computes the girth almost exactly, that is, a +1 approximation. Either we get the girth or a +1 approximation to it. With respect to cycles of even length, previously only polynomial round algorithms were known for this problem, except for the case of cycles of length 4, and it was possible to detect those cycles in a constant number of rounds. We extend this and show that for even cycles of constant length, it's possible to detect their existence in a constant number of rounds. When we go to congest, the story is a little more complicated. First, it was shown that it's not possible to approximate the girth too closely unless one wants to pay at least square root of n number of rounds. Later on, approximations for girth were shown in a sublinear number of rounds, and also a linear round algorithm was shown for computing the girth exactly. Our work shows the first sublinear algorithm for detecting girth exactly, as long as the girth is constant. When it comes to C2K, cycles of even length, lower bounds were shown for this problem. And for the case of cycles of length 4, it was also shown how to detect these cycles in square root of n number of rounds, matching the lower bounds. Later on, it was shown in further works how to detect the existence of longer even cycles in a sublinear number of rounds. And in our work, we improved the result for C6, C8, and C10. And we have reason to believe that the complexity that we get should be the best possible, barring some major breakthrough. However, there are no better lower bounds. And the reason for that is that for the case of C6, it was already shown that several techniques for showing lower bounds, for example, two-party communication, can show better lower bounds than what's currently known. And in our work, we show that the lower bounds currently known can't be improved, otherwise it would imply lower bounds in circuit complexity. Finally, we want to talk about partition trees. Partition trees is a new technique which we present in this paper, and it comes to replace several usages of randomized vertex partitions in other papers. One of the places where vertex partitions was first used with relation to distributed subgraph problems was almost 10 years ago, and they used it for algorithms for any subgraph. Later on, a more load-balanced partitioning was used. However, that was randomized, and it was used for triangles, that is cycles of length 3. And another paper recently used also these randomized vertex partitioning, which are load-balanced. However, not for triangles, but for cliques of any size. It was also shown how to use a similar partitioning, which preserves the same load balancing requirements that were required previously, however, in a deterministic way. And in our paper, we extend this and we show a technique which gives us the same guarantees as this load-balanced vertex partitioning. However, it works for all subgraphs, not just for triangles, and it's deterministic. Okay, so now we'll see an algorithm in the congested clique, which approximates girth up to +1 in a constant number of rounds. Assume that this is the input graph that we have, and this is the shortest cycle in the graph. We want to output either the length of this cycle or ±1. The way that we do that is broken into 2 steps. The first step makes sure that every single node knows the neighborhood surrounding it up to a radius of at least the girth divided by 20. Now this happens for all nodes at once, but for clarity, let's just focus on one node. The challenging part in this step is that we want to do an O of 1 rounds. However, the girth can be non-constant, and so that would mean that some nodes, well, practically all the nodes, will have to learn a neighborhood of radius which is non-constant, and that's very challenging in O of 1 rounds. Once we do this, the second step is an algorithm which takes every single node and doubles the radius of the neighborhood which it knows right up until it almost hits a cycle. And this gives us the +1 approximation. So let's see how we achieve both of these 2 algorithms. For the first one, we recall this very well-known relationship between the number of nodes, the number of edges in the graph M, and the girth of the graph G. Now, we don't need to look exactly at the numbers, but we have to get the general gist, which says that given the number of edges M in the graph, it's possible to compute a very tight upper bound on the girth. Now, given this upper bound, we want every single node to learn its L of M divided by 20 neighborhood. This is our goal, and to do that, we do 2 steps. The first, we list all paths with at most L of M divided by 10 edges. Basically, this is a subgraph listing problem where the subgraph has L of M divided by 10 edges. After we do this, we want to redistribute the information, and we do this using an enhanced version of Lenzin's well-known routing algorithm, which allows us to make sure that we take the output of the first step and make sure that every single node in the graph knows the neighborhood surrounding it of radius at least L of M divided by 20. Now, this second step is a little too complicated for our purposes right now on the slides, and so we'll focus only on the first step. So how do we list all paths with length at most L of M divided by 10? Well, the first question is, let's recall what listing it means. And so listing means that every single one of these paths will be known to some node. So for example, this node can know about this path, and this node can know about this other path. The only constraint is that every single path will be known to some node. It doesn't matter which node, it just matters that every single path is known. Okay, so how do we do that? And to do that, we use the technique called edge partitioning. We take the edges of the graph, and we number them from 1 to m, and then we split them into parts where each part has roughly the same number of edges. Let's, for example, assume that we want to list all paths with length at most 3. So take an example path from the graph which has length 3. The edges from this path come from at most 3 different parts in the partition, maybe these 3, or maybe these other 3. If we ensure that every single choice of 3 parts in our partitioning is under the responsibility of exactly one node in the graph, and that one node which is responsible for these 3 parts learns all the edges in these parts, then every single instance of a path of length 3 will be known to some node in the graph. And so in order to do that, we have 2 constraints. The first is that the number of ways to choose such many parts is at most n. And the second constraint is that every single node, once it chooses this many parts of the partitioning which it wants to learn, and learns all the edges in them, that the total number of such edges is at most O of n, so that this can be done in O of 1 rounds in the congested click. Now the key here is that due to the value of L of m, which was shown before, the Turing number, it's always possible to choose a corresponding value for P of m such that both of these constraints hold. And this basically finishes the first part of the algorithm. This part is very, very trivial and works due to both of these constraints being held no matter how many edges in the graph exists or the girth of the graph. For the second, so now our current state is that we have some upper bound on the girth, and every single node knows the neighborhood surrounding it of radius at least L of m divided by 20. What we want to do now is we want to double this radius up until we almost hit a cycle. And so to do that, assume that this node knows this neighborhood surrounding it. Look at the nodes at the edge of the neighborhood. They also know some neighborhood surrounding them. And they want to convey the information from their neighborhoods to the center node. Basically, this gray node wants to learn all of the edges and all the nodes on this slide. And so to do that, every single green node counts how many nodes it's aware of that the center node does not know. And it sends these values to the gray node. The gray node sums the values, and if it's at most O of n, it can learn using simple routing techniques all of the information on this slide. However, if it's more than n, that means that at least one node was counted at least twice. For example, these 2 green nodes would count the same node twice. And this would mean that some cycle exists in the neighborhood we're trying to learn. In this case, we are able to learn the largest neighborhood possible up until we almost hit a cycle. We don't learn the last node in the cycle. And so this gets to a stage where we don't know if the cycle that we're looking at is either of even or odd length. And so that's why we don't get the exact girth of the graph, but we get a plus or minus 1 approximation. Okay, so that was the algorithm for girth. Now we want to present a technique called partition trees, which overcomes one of the major tools used in the congested click, in the congest model as well, and in many other problems and models in different papers. Now, this technique that we try to replace is vertex partitioning, taking the graph, splitting into the vertices into groups of nodes. Now, one of the major characteristics that's usually looked for is that for every 2 pairs of parts in this partitioning, the number of edges between them is roughly the same. Something which would be undesirable is for two different pairs of parts to have different number of edges between them. This could cause lots of load balancing issues, and that would not be good for us. So we want to overcome this problem. How is it usually done in practice? The common technique to get such a balanced vertex partitioning is to randomize, because if you randomize the vertex partitioning itself, usually you get a very balanced out partitioning. However, this has 2 major drawbacks. The first is, if you want a deterministic algorithm, it becomes a problem. And the second is, because usually you want everything to hold with high probability, lots of log n factors pop up in different places. And for an O of 1 algorithm such as ours, this becomes problematic. So we overcome this problem by creating lots of different partitions. And our partition tree technique does the following. It gets some number, for example, 3. And it creates tons of partitions, even a polynomial number of partitions, such that for any k vertices in the original graph, there's a choice of k different partitions, such that when we look at the parts where these vertices come from in the partitions, the number of edges between these parts is roughly the same as the average number of edges between any 2 parts in any of these polynomial number of partitions. Now, while this is a rather obscure property, it turns out that this property suffices for many different applications. And so in this paper, we show how to use this partition tree technique to build a data structure, which allows us then in O1 rounds to detect cycles of even length, or to improve upon the state of the art for detecting exact girth if we know some properties of the graph, for example, that it's triangle free. So these are two uses for partition trees, which we show in the paper. And after this paper was published, we also discovered additional uses which can improve upon the state of the art in other problems using partition trees.
We turn our attention to the Congest model, where we consider the exact girth and the even cycle freeness problems. One recurring argument in even cycle detection algorithms is that if we're given some node v, it is possible to determine whether it participates in a 2k cycle using order 1 rounds. Roughly speaking, the key contribution of our work in Congest is to give an order of 1 procedure in which the network is given some vertex S, and it determines whether S neighbors a 2k cycle, rather than just participates in it. Using our new cycle neighbors technique, we show vastly improved algorithms for small even cycles and exact girths, as well as present new circuit complexity barriers for improving the currently known lower bounds on C6 freeness. Given the cycle neighbors procedure, we can detect 2k cycles in the following manner. We define a heavy cycle as a cycle with at least one node with high degree, and a light cycle otherwise, if all of its nodes have only low degree. For a heavy cycle, we can sample a neighbor of it efficiently, while for a light cycle, we can collect its neighborhood efficiently. More formally, the algorithm works as follows. We sample n to the 1 minus 1 over k times log n nodes, which is sufficient for sampling a neighbor of a heavy cycle if one exists, and run our procedure on each vertex of S. If we found a 2k cycle, we terminate. Otherwise, we remove all nodes with degree larger than n to the 1 over k from the graph, and each node collects its k-1 neighborhood. This gives an algorithm with complexity n to the 1 minus 1 over k. Next, we'll see some intuition on how the cycle neighbors procedure works. Small disclaimer: for the benefit of time and intuition, this part will contain several inaccurate details. So we said that the network can detect, given a node v, whether it participates in a cycle in order of 1 rounds using a BFS-like algorithm and an additional trick called color coding. Therefore, given a node S, we can check whether it's a neighbor of a 2k cycle by running an independent BFS algorithm from each of its neighbors, and we would like to do this simultaneously for efficiency in rounds. Let's see an example of how this works. Here we have some node S which the algorithm sampled randomly. It starts a BFS from each neighbor simultaneously, where each node propagates all the tokens it's seen so far forward. After k steps, the nodes of layer k check whether they received the same token from two sources, and if one did, it outputs that a 2k cycle was found. The key obstacle of our algorithm: there could be many tokens to propagate in a single round. This is caused by BFS algorithms that interlace with each other. We note, however, that when two BFS algorithms interlace, they create a cycle smarter than the one we're looking for. Here we can see many force cycles which create the interference in the first node of the cycle. Luckily for the exact girth problem, this can't happen, as we're looking for the smallest cycle, which makes our analysis easy. For 2k cycle freeness, this algorithm requires careful and heavy case analysis, in which we show that this can't happen unless there are some easily detectable 2k cycles which are also in the graph. It is worth noting that while our analysis holds for cycle up to size 10, for 12 cycles we have an example with high congestion for this algorithm, which means that in order to extend this algorithm for larger cycles, some new ideas are needed. We've seen results for the girth computation and 2k cycle freeness problems in both the congest and the congested click models. In the congested click model, our two main results are a +1 additive approximation algorithm for girth computation in order of 1 rounds, and the partition trees technique, which allows us to solve both 2k cycle freeness in order of 1 rounds and also allowed us to compute the exact girth efficiently in triangle-free graphs. In the congest model, we've seen the cycle neighbors technique, which gave us faster algorithms for small even cycle freeness problems and the exact girth problem, and also obtained circuit complexity barriers for improving the currently known lower bound for C6 freeness.